Merhaba, we are Iztech Cengaver Rover, a student team based in Izmir, Turkey. Please welcome our second generation rover Barzu, in others say Cengaver 2. We have 30 members in our team from 3 different faculties and 14 different departments. Our team includes 4 technical sub-teams and 2 organizational sub-teams. If we want to extend it, our technical sub-team consists of electronics, coding, mechanics, and science. The organization sub-team consists of sponsorship and design coordination. Our motto is Dream Big, Work Hard, and ERC'24 is a good opportunity for us to represent our ambitions and our university in international area.
ERC'2 features a dependent four-wheel rocker suspension system with rockers interconnected by 4 rod and bearings. The rocker is designed to withstand substantial loads imposed by the robotic manipulator. A specialized unloading method has been used during the rocker's design phase to mitigate landing moments and inertia effectively. To produce lightweight and durable rover, we produce our material from aluminum 6061. Weight of the rover is approximately 50 kg with robotic manipulator and drilling mechanism. The largest dimension of the rover is 95 cm without the antenna. This design enables the rover to navigate extreme terrain and overcome obstacles up to 1.5 times the wheel diameter. With low center of mass, allowing us steep angles up to 45 degrees for slope traversal in the ERC competition zone. Customized TPU95A printed tires enhance traction, while the hub drive system with 2 slim bearing improves rigidity and the power transmission efficiency.
Manipulators weighs 15 kilograms and can reach up to 110 centimeters when fully extended, and has 5 degrees of freedom. Everything is aluminum except shafts. Shafts are chrome strengthened steel. Due to that, our manipulator is light and also strong. For high precision, we use 3.5 Nm stepper motors with 50-to-1 planetary gearbox to actuate the links, and DC motors to actuate the gripper. To decrease the torque requirement of the system, we use the parallelogram mechanism and carried one of the actuators to base and used 3 bevel gears to create a swing mechanism. We are actuating both links at the same axis, with 2 shafts are concentric and supported with bearings between. With this system, we decrease the load on the links and torque requirement of the first actuator. Also, for the minimalized friction, ball bearings and thrust bearings are used. To increase the use of manipulator, we are planning on using hybrid control system, where we control the 5-pipe parallelogram mechanism with inverse kinematics and other axes with forward kinematics.
The control of our rover consists of 2 parts, manual and autonomous control. The control system mainly works with robot operating system, which allow us to communicate between devices and software easily. ROS2 is working with NVIDIA Jetson Nano on the rover. Jetson Nano is mainly operating by Ubuntu 18.04. To implement ROS2 and Ubuntu version on the Jetson Nano, ROS2 is used as a Docker container.
For the development of the web interface software running on Cengaver 2, WebRTC protocol to connect the rover to Vue.js frontend of the rover was used. The main purposes of the web interface is for the rover to be controlled manually and its systems to be controlled via the web. The WebRTC protocol is used to connect the rover's cameras to the Vue.js frontend. The control of the software running on Jetson Nano with the Docker images and the surveillance systems on the rover were developed by the team's great endeavor.
Embedded part is responsible for programming the hardware that the rover uses. The chosen microcontroller is Raspberry Pi Pico, since it has great integration with frameworks such as MicroOS and FreeRTOS. Responsibilities of the microcontroller are controlling the DC models, controlling the robotic arm, and reading the data of all sensors. Quadrature encoders are used for the PID control of the motors to ensure that they work at the correct speed. Inverse kinematic equations are used to control the robotic arm position. And lastly, data from all the sensors are used for science analysis.
To provide autonomous drive, a GNSS model is used to determine rover location. Location information is using with computer vision and SLAM scripts for the rover's autonomous movement. To make SLAM algorithms properly, there is a simulation of rover in a URDF file, which represents the rover physical properties, such as mass and inertia. In an XML file, the simulation of rover was created from an extension in SolidWorks and was set to the joints manually in XML file.
As the electronics team, we aim to establish a stable system. A 29 amp-hour lithium-ion battery configured in a 7 series and 10 parallel setup powers the rover. To operate in dark environments, a modular 100-watt power LED has been integrated into the front of the rover. The battery pack, weighing approximately 3 kilograms, in the main component of the electronic system, meeting the rover's power needs.
A custom PCB was designed to establish connections and install necessary circuits within the rover. During the design phase, particular attention was given to entering important designs for the motherboard. After production was completed, signal integrity testing was conducted and PCBs have been tested separately with target rover parts to ensure proper functionality.
Local Wi-Fi networks were set up on the base station and the rover for secure communication.
Remote control of the rover was enabled using a Tenda B6 access point, allowing communication up to 2 kilometers. A 3 kg, 2.5 meter antenna setup is deployed at the base station.
As Iztech Cengaver Rover science team, we're excited to share our mission approach.
Mars's dust storms threaten rover missions by reducing solar panel efficiency, damaging instruments, and impairing visibility. We aim to build a protective barrier around the rover to maintain operations and precise navigation. Additionally, by drilling into planetary rocks and analyzing their composition, we aim to uncover the planet's geological history as well as access geologically significant materials in the planetary subsurface, which can reveal past hydrological activity and potential biosignatures. Our scientific sampling system comprises three primary components: a drilling mechanism powered by two DC motors with a screw mechanism, a scoop attachment for soil collection, and a specialized containment box. The box has 4 sections, 3 for soil collection and 1 for containment. Upon extraction, it rotates 72 degrees using a DC motor and rotary encoder. Samples are transferred with a high-precision robotic manipulator, and after sampling, the box is resealed and compressed again.
Our scientific mission focuses on 2 primary objectives. Firstly, we employ specific regions to thoroughly examine soil samples for the detection of lipids and proteins, which are crucial biomolecules indicating biological activity. Moreover, we evaluate phosphate concentrations as a potential marker for microbial life using the molybdenum blue method. Secondly, we aim to assess the soil's ability to sustain life by evaluating key ions and soil metrics such as pH, moisture content, and nutrient availability. A variety of sensors featuring the MQ series and atmospheric sensors are utilized. These sensors enable us to detect gases such as ammonia, carbon monoxide, methane, and carbon dioxide, analyze soil composition, and monitor atmospheric conditions, providing valuable insights into environmental conditions and potential habitability.
Furthermore, we utilize a custom-built visible spectrum spectrometer. Our spectrometer is designed to provide high-resolution data that's essential for the analysis of geological rock samples and comprises 4 key components: a light source, sample cuvette, light-grating mirror, and detector. The detector measures the intensity of transmitted light, enabling the precise determination of metalline concentrations based on our established calibration curve.